We are on to the second lecture of the series entitled Solid Angle. Let us outline the essential features of lecture 1. Consider a line OA and this is another line OB, and theta is the included angle. Theta represents the inclination or relative orientation between two lines. This theta is a planar angle. Draw an arc AC of radius OA equal to R. OC is R and arc length is L. Now theta is arc by radius, that is L by R. Let us draw a line OP and another one OQ. PQ is an elemental arc DL that subtends elemental angle d theta. OP is R, OQ is R, d theta is dl by R, dl being the arc and R being the radius. This theta is the angle shown and d theta is the infinitesimal angle or elemental angle. Consider line OQ. Another inclined line is OP. From a point, say this one, we drop a perpendicular, call it AB. Then this angle theta is defined through its tangent as tan of theta equal to AB by OB, where AB is perpendicular and OB is the base of the right angle triangle OAB. Consider a closed curve C and O is an internal point. Angle made by C at O is 2 pi radian, which is 360 degrees. This was proved in the previous lecture 1 by constructing a circle with O as center. We considered a line like OA, another one OB that intercepts arc AB on the closed curve C, a small portion of C, and an arc PQ, which is the length on the circle drawn. As the arcs AB and PQ both subtend the same angle at O, we integrated over the circle and we got the result that a closed curve makes 2 pi radian at an internal point. Let us now move over to solid angle, also referred to as three-dimensional angle. It is a supplementary quantity, not a fundamental or derived quantity. Solid angle is angle in 3D space. To make things easier to grasp, let us reach solid angle starting from an angle, that is by making a switch over. Let us consider the point O, draw line OP of length R, construct arc PQ. Now we join all the points on the arc PQ to O. This is how we do it, and in the process we generate the angle theta, defined as arc PQ, that is L, divided by the radius OP, that is R. So theta is L by R. Make a switch over by multiplying denominator as well as the numerator by length, so that essentially we are not changing anything, just switching from 2D space to a 3D space by introducing an additional length, and rewrite theta by capital omega. This is what we get: omega equal to L into L, write length as L, divided by R into R, write length as R. Since length into length is area, this is equal to area divided by R square. Let us consider a point O and a curve PQ. We draw another curve P prime Q prime, join QQ prime and PP prime to form an area PP prime Q prime Q. Join points of the curve PQ to O, then the points of the curve P prime Q prime to O. Next, points of the curve QQ prime to O, and also the points of the curve PP prime to O. That is, we have connected all the points of the contour of the surface PP prime Q to O. This generates a three-dimensional angle that we denote by capital omega and define as solid angle subtended by the surface PP prime Q at a point O. Another example. Take a rectangular surface area. This is the contour, and O is a point located here. Name the contour ABCD. Join the points on the contour to the point O. The three-dimensional angle created at O by the surface ABCD is omega, called the solid angle. Let us take another example. This is a sphere, and let us demarcate an area on top of the sphere, maybe a circular patch. It can be of any other shape also. Let us think of a point here, say O. Join O to the points of the contour of the demarcated area. And this is the 3D angle, or solid angle to be precise, created at O by the patch of surface. Call it omega. This is a hemisphere and P is a point. The hemisphere has a contour. Let us join the points of contour to P, and we get a solid angle here at P created by the hemisphere. Call it omega. Let us now give the formal definition of solid angle. Consider an arbitrary surface S. This is S. Contour of S is C. This is it. Obviously, S is an open surface that we have considered. O is a point near S, say here. Let us join points of C to O, and this is how we join to create a solid angle omega subtended by S at O. Now consider an elemental portion ds of S. Join contour points of ds to point O. This is how we do it. And this is the solid angle created. Call it d omega. So d omega is the elemental solid angle subtended by ds at O. So what will the total solid angle omega be? It would be integration over s d omega. We now find expression of solid angle. Consider a surface element vector dA equal to dA r hat, where r hat is a unit vector normal to area vector dA. Draw the surface element dA, and so area vector dA is dA r hat. This surface area vector dA is located at point P. Let us show r hat. This is it, normal to dA surface element. Let us extend it and consider a point O located on this line r hat. In other words, let O be a point on r cap at a distance r from P, where area vector dA is located, that is OP equal to r. This is the contour of area vector dA. Join contour of area vector dA to point O, and let us do it. The solid angle created is d omega. Elemental solid angle d omega is created by area vector dA at point O. So d omega by definition is dA by r square. Let us make a gist of what we did to find expression of solid angle for this special case. We took P, a point where area vector dA is located. O is a point where area makes solid angle d omega. Join OP. In this case, OP is normal to area dA. then d omega equal to dA by r square. Let us show it once more. This is the area dA at P. Point O is here. Join OP and we see that OP is perpendicular to DA. Join contour points of DA to O and we get d omega equal to dA by r square. Here OP equal to r. The same expression is true if point O is on the other side of the area, say here. Join O to P and here too OP is normal to area dA. Joining contour points to O gives solid angle d omega equal to dA by r square. Obviously, the expression d omega equal to dA by r square is not a general expression. Let us find the general expression of solid angle. Consider a surface element vector ds equal to ds n hat at point P. This is the elemental surface located at P. This is n hat, the unit normal to ds. To represent it easily, let us designate it as S1, S2. Let O be any point and it is here, say. OP is R. This is OP which is of length R. Join the points of contour of ds, that is S1, S2 to O. And this is how we do it. This is d omega. Elemental solid angle d omega is created at O by surface element vector ds, that is S1, S2. Now OP cap, let us call it r cap, and it is the radial unit vector. Let us draw it, and this angle between n hat and r hat is theta. Clearly n hat is inclined to r hat at an angle theta. Evidently, we are considering a general case, and if theta equal to 0, we would move over to the previous special case where point O was situated on the normal to the area. Construct an elemental area vector dA equal to dA r hat perpendicular to r hat, and we show it. This is the area vector dA equal to dA into r hat. To represent it easily, let us designate it as A1, A2. So area vector dA is A1, A2. Area vector ds and dA both subtend the same solid angle d omega at point O. Note that area vectors ds and dA at point P are elemental, that is infinitesimally small, and the angle they subtend at O is thus also elemental or infinitesimal. We are in a position to write the answer for the elemental solid angle d omega. It is by definition d omega equal to dA by r square. For ease of reference, let us designate the area element dA as A1, A2. It is constructed at P where we have ds also. R hat is its direction. This is point O. Join all contour points of dA to O. Same solid angle d omega is created at O. Let us recast this expression in terms of ds. This is the area A1, A2 at P. This is r hat perpendicular to A1, A2, that is to area dA. Join OA1, OA2, which are the edges of the solid angle. And this is S1, S2 vector area, that is area vector ds at P. The angle between the area A1, A2 and S1, S2, that is between dA and ds, is say theta. To make the diagram simpler, let us redraw it. This is A1, A2. This is point O, and let us draw S1, S2 here. That is by making the points A1 and S1 coincident. The angle between them is theta. Now cos theta equal to base by hypotenuse, that is a1 a2 divided by s1 s2. In other words, it is dA by ds. This means dA equal to ds cos theta. Now from figure, it is evident that n hat dot r hat is cos theta. So we replace cos theta by n hat dot r hat. Again, ds n hat is area vector ds. So dA is equal to area vector ds dot r hat. Hence d omega equal to dA by r square equal to vector ds dot r hat by r square. This is equal to ds n hat dot r hat divided by r square. This again is equal to ds cos theta by r square. This is the expression of elemental solid angle. If ds is a part of surface S, then omega is equal to integration over S d omega, which is equal to integration over S ds cos theta divided by r square. If S is a closed surface, then omega equal to closed surface integral over S ds cos theta by r square. If theta equal to 0, then normal to surface element considered, that is n hat, is equal to r hat, which is the radial unit vector. Let us show such situation in a diagram. Let us give illustrations where this occurs. This is the area element. This is the normal to area element n hat, and call the area vector ds. The area has been considered at point P and O is a point. This is solid angle d omega. This case where O is on the normal corresponds to theta equal to 0, n hat equal to r hat, and so area vector ds equal to dA r hat. In fact, ds is dA here. So d omega equal to dA by r square, since cos theta equal to cos of 0 equal to 1. So we can write it as ds by r square also, since dA equal to ds. We give another example where theta is 0. Consider a sphere. Let us consider a circular patch of area upon the sphere at point P. O is the center. Join OP, and this is the radial unit vector r hat. This is area vector ds equal to ds n hat. The solid angle created at O by the circular patch is this one, d omega equal to dA by r square, which can also be written as ds by r square, since dA equal to ds. Let us wind up, make a gist. For this simple case, area vector dA equal to area vector ds and d omega equal to dA by r square. In general, area vector dA equal to area vector ds dot r hat. Hence d omega equal to area vector ds dot r hat by r square. Let us show it once again. This is the surface S, ds is the surface element. Let P be a point. This is how the solid angle is generated by ds at P. Call it d omega. Let us construct the area dA perpendicular to the radial unit vector. Then d omega will be dA by r square, where r is the distance of the location of area and the point P. And this is ds cos theta by r square, where theta is the angle between two areas ds and dA. And this is the radial unit vector r hat, and this is the normal unit vector to ds, which is portion of S. The angle between n hat, the normal to ds, and r hat, the normal to dA, is also theta. Solid angle gives the measure of how much region of an object is exposed to a point. Solid angle gives the field of view of an object with respect to a point. Solid angle has the expression of d omega equal to dA by r square equal to area vector ds dot r hat by r square. Let us find the dimension. D omega equal to dA by r square. Now dA has dimension L square, r square has dimension L square. They cancel out to give m to the power 0, L to the power 0, t to the power 0, where m is mass, L is length and t is time. So solid angle is dimensionless. Now about unit. D omega equal to dA by r square. So it is like omega equal to a by r square. Construct a sphere and consider a circular patch on the surface. O is center. Join contour of the circular patch to get the solid angle omega at O by the circular patch. Suppose area of the circular patch is A equal to r square. Omega equal to a by r square, which turns out to be r square divided by r square. Cancellation gives 1 and the unit is steradian denoted by SR. So we have in the process defined steradian. 1 steradian is the solid angle subtended at a distance r by a surface having area equal to distance square, that is r square. In the next video, we will concentrate on problem solving involving solid angle.